speak at least for introduction, but happy to introduce Bruce Reznick from Urbana. Going to talk about, I forget your title,
I don't,
something.
something.
Quadratic Forms.
Okay. Sense of powers of forms. Thank you. It's very nice to be back at Purdue. The last talk I was here, as near as I can figure out, the date was January 30th, 1979. It was right after the Biloxi joint meetings. I was at Berkeley as a postdoc, having been at Duke. I was applying for jobs. I had interviews at Illinois and at Ohio State, and another refugee from the Duke Math Department, Philip Trotter, was on the faculty here at the time, and he invited me to just give a talk, not a job talk, just give a talk and visit. As one of these things that happens, my office mate during my year at Berkeley was Harold Donnelly, so there are all these connections. And Sam Wagstaff was on the faculty of Illinois at the time. So. I should say to people who haven't heard me talk before that I'm not really an algebraic geometer. And probably the best way to describe me is that I know different things. And I sometimes say that this is the group I belong to, École de Calcul ad hoc, which is sort of perhaps a vanishing breed. It helps to grow up at a time when there are no computers and you have to learn to do computations yourself. I would say there's no real texts in the area, but the closest one to a standard text would be Polya-Zago, Theorems and Problems and Analysis, which despite the title has a lot of things that would be of interest to people in algebra and combinatorics. So I'm interested in three questions today. Well, first of all, I will always talk about forms, and primarily these would be forms over C in n variables of degree D. And this is a vector space of dimension, that number, just by identifying P with coefficients of P. And the first, and I'll also say fairly regularly, that this form is just the way of. And as you know, as the way talks go, the first part will be general and something that lots of people know about, which is trying to find the best way to write P as a sum of powers of linear forms. It's a very classical problem. The second problem that comes up is when n is 2, and the most important work here was done by Sylvester in two papers that today we would consider related, but he apparently did not consider related at the time. And then finally, I'll talk about quadratic forms and most of what I'll be talking about will be sums of 2 or 3 cubes of quadratics and writing sextants as that. So, I said I wasn't an algebraic geometer, and there's actually one simple test that determines, in my mind, whether you are a true algebraic geometer or not. And I failed the test, but probably most of you will pass it. So suppose you have a map, a polynomial map. So you've got P1, x1, xn, Pn of x1. Then the theorem is that there is an alternative, a very strong alternative. Either the PIs are algebraically dependent and f of Cn is contained in some manifold. Either they're algebraically dependent or the PIs are algebraically independent, in which case f of Cn contains Cn minus some other manifold. Now, if you were an analyst, this is an astonishing theorem. But most of the algebraic geometers I've talked to over the years say, yeah, okay, no big deal. Let me illustrate where this comes up in this problem in a very simple example. Let's consider writing binary quadratic forms as a sum of 2 squared. Then, looked at properly, this is a map from 3 variables to 3 variables. And we're in the second case. A is a squared, b is a b, and c is b squared plus c squared. And you don't get everything here, because if a is 0, then b has to be 0. X, y doesn't have a representation like this. But in general, a binary quadratic form could be written this kind. And this is an example of a canonical form. Now, there is something which was called a long time ago the Lasker-Wakeford theorem. I don't know if that's really a term in current use. And what it said was that basically, and at this point it's hardly a theorem that needs a name, it says if there's one point of the map where the Jacobian has full rank, you're in the second case. That's the way it would be interpreted today. Now, it's worth saying a little bit about who Lasker and Wakeford are, especially if you've never seen the names. Lasker, 1868 to 1941. This is Emanuel Lasker, who was the world chess champion from, I wrote this down, 1894 to 1921. He also had a PhD from Max Noether at Göttingen and was a commutative, we would call him, I think, a commutative algebraist today. He did some math work. He was not at a university because he could make a living as the world chess champion. Wakeford, on the other hand, his years were 1894 to 1916. And if I told you that he was British, you would probably get a very terrible idea of what happened to him. He was killed during the First World War, and there's one of the most amazing things I've ever read in a math journal was an obituary for him that was written by J.H. Grace, who was Wakeford's professor at Oxford. And this was written during the First World, while the war was still going on. Wakeford was slightly wounded early in 1916, and soon after coming home was busy again with canonical forms. He discovered a paper of Hilbert's which contained the very theorem he had long been in want of, first vaguely and later quite definitely. This was in March. April found him full of the most joyous and reverential admiration for the great German master, working away in fearful haste to finish the dissertation. He returned to the front in June and was killed in July. He only needed a chance. He never got it. If these sentences had been written about a poet rather than a mathematician, this would be a very famous quotation. But in any case, people were interested in canonical forms, and if you look at this, and count degree considerations, if you have a chance to have a canonical form here, then you need to have this inequality. You need to have at least as many coefficients going in here as you want to be in the output. And a very interesting thing that was discovered by Klepsch in the 1850s is that if n is 3 and d is 4, you have 15 here, and you would expect 5, but 5 doesn't work. You need 6. And I want to explain that using another very old idea, which becomes much simpler.
Bruce, this Lasker-Wakeford theorem is which one? This statement?
The Lasker-Wakeford theorem was the theorem that said that if you have one point where the Jacobian is full, and the way he interpreted it was that if you have a proposed canonical form, and there's a particular value where when you take the partials, they span the space, then it is a canonical form.
So Bruce, is it okay to think about these canonical forms as generalization of diagonalizing quadratic forms?
Absolutely. Though with quadratic forms, the count is off because the orthogonal group acts on sums of squares. But if you had sort of an upper triangular diagonalization of quadratic forms, is a canonical form for the quadratic forms. So what I want to talk about now a little bit is apolarity. And this is a mixture of things. I found a lot of my ideas, a lot of the ideas I'm going to talk about here were expressed in a slightly more sophisticated form by Helgeson. But before I did it, so I can't. This is all pretty old. So let's suppose that we have a form, a complex form. I'll call it H. Let's associate to it the differential form, which would be the same coefficients but each variable is replaced by a differentiation. And this was the one that people studied most, but obviously harmonic functions are important. Now let's suppose that the degree of H is E. Here's a nice theorem that says that if you take a differential operator H of D and apply it to a linear form, what you get is a bunch of coefficients here. And then you get H evaluated at the coordinates of this point. And I don't know if this needs a proof or if this is familiar. If it needs a proof, it suffices to prove for H being a monomial and then it's additive. And for a monomial, what you're doing is you're differentiating with respect to x1, j1 times, and that turns down alpha 1 to the j1 from the chain rule. And it just comes out very nicely. Okay, now, by the way, if E is bigger than D, of course, this is going to be 0, but then this factor here is 0, so the fact that's negative isn't a problem. Now, if the degree of H is equal to the degree of P, and this is where I ran across it, H of dP will be a number, and this gives a very natural bilinear form on the vector space. And if I threw in complex conjugates, which I don't want to do, it would be a Hilbert space, but you can use all of the linear algebra to make some very strong statements. And then the principle of apolarity is, suppose P is the form of D, and suppose H of D, well, okay, H of dP is equal to 0 if and only if P can be written as a sum of linear powers where each of the coefficients come from the variety of H. And here the only condition is H has no repeated factors. And there's a very simple proof that would not have been accessible to the 19th century, and I don't really know how people did it in the 19th century. So here's the proof. Let A be the set of everything that's like this, and and let B be the set of P such that B is 0. Well, A is contained in B by what I did over there, because if I take H on a sum, H of alpha K is 0, so everything's vanishing. So now I want to look at the perps under this bilinear product. What's a perp? That's a set of P so that P, the inner product of P with one of these guys is always 0, which is the set of P so that P of alpha K is 0 for any possible alpha K. In other words, H equals 0 implies P equals 0. And by the Null-Stellensatz, I know some things, but not many, this implies that H divides P. If H is an irreducible form, and then you can combine the different irreducible forms. Okay, so suppose P is an A perp. I want to show that, well, let's say G is an A perp. I want to show that G is an B perp. Well, G is going to be H times something K, and when I take G of B on something in B, that's going to be K of D acting on H of BP. And because I'm already in B, this is 0. So what this means is that A is in B, A perp is in B perp, so A is equal to B and A perp is equal to B perp. That's kind of a nice argument, but I have no idea how the 19th century people were able to do this without knowing vector spaces or really Null-Stellensatz. I don't know whether the Null-Stellensatz had been proposed and just not proved by the earlier algebraic geometers. Okay, so Clebsch. Ternary quartics. AKX, AKY, CKZ, fourth, and then you want to write this as P of X, Y, Z. What Clebsch said was this: let's take a typical P, let's take a typical H, which is going to be, let's say, alpha 2, 0, x squared, a quadratic form. There's 6 coefficients here. If I take H of D on P, I get 6 linear equations on the coefficients. And there's 6 coefficients, so in general, I can't solve it. On the other hand, if I have a sum of 5 fourth powers, there exists a conic phi, so that phi of AK, BK, and CK is 0. CK going from 1 to 5. This is because any conic is determined by 5 points. So that means that a general P can't be killed by a quadratic, but every sum of 5 fourth powers is killed by a quadratic. Now Sylvester did that in a somewhat different way. He looked at H squared of D on P. There's a lexical reason I'm bringing this up. So this gives a quadratic form in the alpha ij's, whose coefficients based on the coefficient of P give you a 6 by 6 matrix. And then if you're a sum of fourth powers, that matrix has, each fourth power gives you a quadratic form of rank 1. So a sum of 5 fourth powers has only rank 5, and it's in general a 6 by 6 matrix. And so that's not the general case. Now, the term that Sylvester used for this is one which I know has lived in algebraic geometry. That was the original catalecticant. And I would like to read an apology that Sylvester made. He said, that's wrong sheet of paper, another sheet of paper here. Mi catalectic Kaisand would more completely express the meaning of that which, for the sake of brevity, I denominate the catalecticant. The term comes from something in very technical verse, which is where that comes from. But in fairness, the same paper in which he introduced the term catalecticant, he also introduced the term unimodular, which I think has had a somewhat better lifespan. Okay, well, another talk would spend more time on this, but ternary quartics are not the unique counterexample. There are 4 classical cases where you need to go a little further than what you did. And then Alexander and Hershowitz, about 20 years ago, proved that those are the only such cases. I'll mention a small result of mine, which is that if you look at a quadratic squared plus a sum of 3/4 powers, this has 15 coefficients, this has 15 coefficients, and this actually is a canonical form. So at this point, I think in the interest of time, and definitely time and interest, I'm going to move on to binary forms. And binary forms is something that's, Sylvester invented an algorithm, although I'm sure it would not have been called an algorithm at the time. Let me write out a binary form like that. And you want to know when P can be written as sum of forms like this. Using a polarity, you would define h of xy, the product of beta j x minus alpha j y. This would be a form that would vanish at these, when we assume that alpha j beta k is not equal to alpha k beta j. And then if you write this out as, let's say L goes from 0 to R, CLX to the R minus L over the L. If you compute h of d on P, you get a beautiful matrix. So the condition that this holds is that you have a non-zero solution to this linear system. So given any particular binary form, you can just write down the a's and wait until you get a polynomial that factors into distinct b's. Now, if you do this with cubics, you're looking at this system, you're getting a quadratic. The condition that it works is precisely that the discriminant is not 0. And the fact that if it factors over it, so this is what you actually get as the discriminant of the quadratic is minus delta over 27, where delta is the discriminant of the cubic you started out with. Now what Sylvester did with this was to say that if D is odd, there's always a solution. So a general binary form of odd degree is, of odd degree 2k plus 1 is the sum of k plus 1 powers. And if you look at the numbers, k plus 1 powers times 2 is the number of terms in a binary form of degree 2k plus 1, so this is a canonical form. For even degree, you've got a problem. But then he said, well, let's play around with A0. Let's take away a multiple of x to the 2k, and then you can generally find a value of lambda for which the determinant is 0, so you have a solution. This is what Sylvester wrote about that. I discovered and developed the whole theory of canonical binary forms for odd degrees, and as yet made out for even degrees too, at one evening sitting with a decanter of port wine to sustain nature's flagging energies in a back office at Lincoln Inn's Fields. The work was done and well done, but at the usual cost of racking thought, a brain on fire and feet feeling or feelingless as if plunged in an ice pail. That night we slept no more. Italics in the original. Now, I should explain that because of British anti-Semitism, Sylvester for a long time was not able to have an academic position, and he was working as an actuary in a law firm in London when he was doing this. And he had the great good fortune that there was another mathematician who was working as an actuary in the office next door, and that was Cayley. Those two were better mathematicians than any academic mathematicians who were working at the time. So okay.
quick question. Does this algorithm run in polynomial time in the size of the input?
Well, if you input A, there are a finite number of matrices to check. The tricky part comes in making sure that the discriminant of the solution is not, that you don't have repeated factors. But this does run very quickly. Now, I'll mention that what I did a few years ago was to observe that if you restrict yourself to a field, that's a subfield of C, the theorem goes through absolutely correctly. So it's quite easy to believe that a polynomial, a form, might have what's called a different relative rank depending on the field that you're looking at. Let me take a quick example, and then I'll give an advertisement. This is real. It's obviously a sum of 2d powers over c, but by something I'm going to say in a moment, it's actually a sum of no fewer than d powers if you require real coefficients. Okay, Sylvester, this algorithm was 1851. In 1863, he was trying to work on a generalization of Descartes' rule of signs that was related to one of Newton's rules for roots. And the implication of his theorem was that if P is real, degree D, not a d power, and has S real linear factors, and if P is a sum of S real, T real sum S, then T is greater than or equal to S. And it's a relatively straightforward implication from this to imply that if P is entirely a product of real factors, then it has to have length D. And I had a number of people asked a few years ago whether the converse was true, and that's been proved by Greg Bleckerman and Rainer Sin, that the converse is true. And there are a lot of people involved, and I don't have the time. I have it written down in a paper, but this was maybe 6 or 7 people were working on this recently. Now I'd like to give a brief advertisement for my PhD student, Merriman Tokchan, who is finishing this year, and this is from a paper that was been on the archive for about 5 weeks, submitted for publication. If we let L denote the relative, I call this in one of my papers the length, but everybody else calls it the rank, so I'll call this the relative rank. This will depend on the field. This is a real polynomial, but any Actually, it's a polynomial over Q, but any polynomial, any field between Q and C, you can compute this value. By Sylvester's theorem, this is 2K. K is greater than 3, and I published a few years ago a form that has 3 different lengths, but a specific one of degree 5. This is generally the case, and for odd degree, you take x to the k1 to the kx minus y. So for every degree at least 5, there's a form, and a fairly simple one, with 3 different relative ranks. And the natural and open question is, can you do 4? We don't have a good answer for that. The other point I want to make about Sylvester's theorem is that Sylvester, if he were alive today, would have noticed that there's a connection between this and the theorem he had done on forms over C. He made no remark to that, and I think the reason is twofold. His original version was about polynomials, not about forms. And he was talking about reals and complexes, and of course the idea of a base field did not exist 150 years ago. He probably would have been surprised if someone had pointed it out to him. Okay, let me move on now to quadratic forms, and first list a conjecture of Boris-Shapiro. It's a wonderful conjecture. So from now on, everything's over the complex numbers, everything's a binary form, so in theory, there's nothing to worry about. So suppose the degree of P is D times E, and we want to write P as a sum of d powers of forms of degree E. Boris-Shapiro's conjecture is that you can always do D. This is not a canonical statement. It's easy to prove this as a canonical statement, and even to do a little better than that. But this is true without exception. So let's look at some simple cases. Well, when D equals 1, there's nothing to prove, if you think about it. When D is 2, the degree of P being 2D means that P can be written as a product over C of 2D linear factors. And this means I can group them into 2 factors like this. And when I started moving from functional analysis, which is what my thesis was in, to algebra with T.Y. Lamb when I was a postdoc, around the time I was giving the talk here in 1979, this was one of the first things I learned, that to an algebraist, a sum of 2 squares is the same as a factorization. So that gets D equals 2 automatically. When E is 1, that actually is a consequence of Sylvester's algorithm, and it turns out that L1 to the D minus 1 L2 can only be written as a sum of D powers and no fewer than that. If you want to know the reason, the matrices tend to look like this, which means that any null vector will have 2 consecutive zeros, which will require a square factor until you get only 1 row, roughly. If I could shrink time, I could give you more of a proof. So the first case that's natural is D equals 3 and E equals 2. And I'm going to give you a sketch of why that's true. But you'll have to believe me on a few things. And, well, I have to believe mathematical also, so it's the same. So let's suppose that P is a sextic. Let's say P is a non-zero sextic. So we can write it after a change of variables which doesn't affect I'll put binomial coefficient like this. And we can assume that A0, A6 is not 0 by making a change of variables if necessary. Okay? So one of the things I learned at École de Calcul ad hoc is that if I take P and subtract this particular cubic from it, I agree on the coefficient of x to the fifth y, and x to the fourth y squared. So this is y cubed times a cubic. And then you use Sylvester's algorithm to write the cubic as a sum of 2 cubes. And you have your 3 cubes. Now this might fail. And you can calculate the discriminant of this polynomial based on the AIs, and you get a polynomial of degree 18. It's a non-zero polynomial, so generically it's true. But that's not what Boris Shapiro's conjecture is. His conjecture is that it's always true. So what do you do in that case? Well, let's look at when this doesn't work, what do you have? I'm running out of letters to use comfortably. This would be an example of something where the algorithm would fail. Now what you do is you send x to itself and y to tx plus 1, which is an invertible transformation. Calculate a new polynomial, calculate the discriminant of what you get there, and what you have, let's see if I have this written down properly. You get a polynomial of degree 72 with tens of thousands of terms. I do not trust Mathematica's solve, but I trust its computation of the polynomial. So I actually took 4 or 5 of the coefficients with the smallest number of terms and worked out that the only way that that polynomial of degree 72 would be identically 0 would be if I could get a sum of 3 cubes some other way, in some special case. And what that means is that except for 72 values of t, what I get here will get this as a sum of 3/6 values. So that answers the question, perhaps not in a completely satisfying way. And if you try to do numbers on this, the numbers are horrible. If I had done this with a Beamer slide rather than a Blackboard talk, you would have seen some of the examples, but I don't want to spend a minute or so. You can take a very innocuous looking polynomial and get a representation that involves a quadratic field that's the square root of a 5-digit number without much effort. But the last thing I want to talk about is one where...
Do you believe the conjecture is true?
I think the conjecture is true. I have no idea how to prove it. This 2 quadratic forms that you'll see in a moment have some very special conditions that you can't expect to hold for more than that. The next case would be an optic as a sum of 4 fourth powers of
Do you know what was the motivation?
I'm sorry?
What was the motivation of Boris?
I'm not sure. But he said, I've been told this is sort of a question you'd be interested in, so.
Yeah, he's coming from time to time with some really strange conjectures that for some reason happen to be true.
Well, this one, actually, this is part of joint work that'll be with Boris and Hal Schenk, but I haven't seen anybody's work other than mine in this, so I don't know exactly what its status is. Let me leave with a simpler, I'm not quite done with this, but this was one of my original motivations for looking at this. Maybe somebody told them that I had done this and thought I might be interested in it. So let's say you're interested in writing a sextic as a sum of 2 cubes. There's 6 coefficients here. There's 7 coefficients here. you have, in fact, 7 polynomials in 6 variables where the degree is 3. Now, the proof of the Hilbert basis theorem would say they have to be algebraically dependent. Because let's say you take a form of degree d in these, you will have d plus 6 choose 6 forms in 6 variables, but they're going to live in the forms of the 6 variables of degree 3D. And eventually, this is going to be bigger than this. Mathematica tells me the first time this happens is at 1442. That's not very good. I asked Dan Grayson once to compute this, and it crashed